Hi everyone, my name is Ege. This week I will present the third part of the Kato Theorem. In the previous presentation, Arash introduced us to kinetic energy operator, its domain and self-adjointness of T0. This week we focus on the potential energy. Before I started the potential energy, I briefly recap the definition and the properties of the operator AI. Then I will proceed to prove the lemma that we encountered at the end of the previous session. The operator AI is defined on L2 and AI FRI is equal to square root of the integral of FR. But please notice that we are not taking the integral with respect to each component of the variable r. And for all I from 1 to s, we have the norm of AIF is equal to norm of f, absolute value of AIF minus AIG is less than or equal to AIF minus g, and the absolute value of AIF minus AIG is bounded by the norm of the difference of f minus g, f and g. And the lemma says that when f is in the domain d0, for all I from 1 to s, we have AIFs are continuous, they are positive, and bounded by a prime, norm of t0f plus b prime norm of f. Here a prime and b primes are constants. They are independent of f, and we can take a prime as small as we want. The proof is quite long but not too complicated. We divide the proof in two parts. In the first part we show that this inequality is true for any g in the domain d1. And the second step, we extend the domain from d1 to d0 such that this inequality is true for all f in the domain d0. Let's start to prove the first one. Since the proof is same for each I, we just consider the case I is equal to 1. We are taking an arbitrary g in the domain d1 and our g's are of this form. Now we are taking the square of the norm a1g, which is equal to, by definition, integral of the norm of the square of the norm gr. In the next step, we apply Parseval identity to variables from r2 to rs. Then we get this equality. Since the absolute value of the integral of f is less than or equal to integral of the absolute value of f, we can write this inequality. On the other hand, we show that this integral is bounded by the multiplication of this integral and the integral of 1 over 1 plus k to 4 p1 to 4 for some constant, for some positive constants k. When we take this integral with respect to p1, we get this integral will be equal to ck to minus 3 for some constant c. When we integrate this integral with respect to dp1 and dps, we get that square of the norm g and k to the 4 square of the norm p square, p1 square g.